Hello everyone, it's February 22nd again. Alright, the second one for today. Well, it's not really a second one. We're going to do this, we'll go back to the night schedule. And I want to do it a bit earlier because it has been very rough, right? Doing it really late. I got really tired, got really sleepy, and not really into it. So I'm going to do it earlier. 7 seems to be a good time. 7 o'clock is when the next day releases for me at least, right? So we are just going to try that. As it's opening, let's try the other one. 133. I've done this before, but I don't remember. Clone a graph? Is that what it is? Clone a graph. %45 passing rate. Not too bad. All right, so let's take a look. Clone a graph. I was trying to open another problem, but it was very slow. I just tried this one. Oh, October on one attempt. Given a reference of a node in a connected undirected graph, return a deep copy of the graph. Each node in the graph contains a value and a list of its neighbors. Okay, each node's value is the same as the node's index. One index, for example, the first node with this, the second node. Okay, the graph is represented in the test case using an adjacency list. That's fine. I don't have to read this. Even though it will always be the first node with value 1, you must return a copy of the given node as a reference to the cloned graph. Example 1. Original graph. You can't return the same graph for sure. This looks like a clone. The nodes are new. Graph looks the same. The nodes were cloned, but the graph is messed up. Doesn't have the same connections. Yes, yes. Okay, so read more carefully. So I have 100 nodes. Value is unique. Okay, there are no repeated edges and no self loops. Graph is connected, and all nodes can be visited starting from the given node. So, I mean, we can do BFS or DFS, right? How would you do DFS? Well, we're going to create the root of the node, and then we pass it in. And as I traverse, because each node I traverse all the neighbors, right? I traverse all the neighbors. And for each neighbor, I will create a new node and traverse on that, right? And but we have to keep a record, so which one has been traversed already, right? So we don't do it repeatedly. Well, actually, if you think about it, this might not be easy to implement in this DFS. Because for one node, I have a bunch of neighbors. Well, actually, I can create, right? I can create a bunch of neighbors. And then from this one, I just go with each one, right? Go with this one. And if I end up at a node, so like this will be next. Will be this. Well, how do we? Yeah, how do we do in DFS? Well, if we want to do a DFS, if a node has been processed, like we can like set the original value to 0, all right? And then if the node has been processed, which means it has been cloned, we set it to the value. If it's not, like if I haven't done it yet, and we don't, and then yeah, I'm just thinking, what if I link them back? All right, I say this one is a link back. How do we handle this? Yeah, actually, I don't know. DFS doesn't seem to be. I think I'll go with BFS. BFS will be easier to handle, I think. BFS have the root, right? I have the root, and then again, I have all these, and I put all these, and then we go to this, and then we go to this, and we have all its node. And if it's node, but how do we link back? Well, it's the same problem, right? It's the same problem. No matter it's DFS or BFS. Hold on. So like this, 1, 2, 3, 4, right? So I have this, okay, and then I say this node has two neighbors, and for this, for each one, we will create one, connect, right, and then this will push its next one, right? This will be the next one into the queue, and at 3, we can push this one out, and this will go to the next queue. And now 4 comes out. How do I know which one should be connected to 4? Hold on. So I have this. We pop out, right? And then we find its neighbors, right? We find its neighbors, and for each neighbor we find, we push that into the queue, and we make the connection, and we put that into the queue as well. We have 2 queues, right? And then on the pop out, okay, this one pop out, and we will find all its neighbors, right? Find all its neighbors, and its neighbor, if it's something that we have considered before, right? If it's something that we have considered before, then we ignore it. If its neighbor is something we have not considered, we push it in. If something we've not considered, because this is what we're looking at, right? And then we need to make the connection. How do we know the connection? Hold on. We can traverse the graph. Okay, we traverse the graph, and we traverse the graph. And every time we have a connection, we just make the connection, right? Every time we have a connection, for a node I have all these connections, and then I will reflect it on that. We have all these connections. Okay, so this seems to be a. I have an idea, but it's different. It's just I will create an array because I want to address, like I need to address a node immediately. And as I traverse through, every time I find a node, I go to all its neighbors, right? And I want to make the connections in the copy, right? In the copy, and then I go to the next one, and yeah, and if it's that, we have all these. So for each node, right? for each node, we have to go. It's undirected. Undirected. Hold on. It's undirected. Yeah, so it has to have all its neighbors, right? For me, if I go here, right, if I have my neighbors this, then I have to do everything. And then, yeah, basically means if the node, if 1 go to 2, right, so and I might want to go to 2 and 2 have to point back to 1, right? And then from 2, then I can say, oh, everything has visited before, I don't have to check, right? I don't have to check. And then I have a new one, right? From 2, let's say I go to 3. But 1 also go to 3, right? So 1 and 2 both go to 3. But I created 3 right now, but if I say 2 needs to point to 3, I cannot. If the 3 is not addressable, if the 3 is like living in a queue, how am I going to address it? So I can't. Therefore, the only way is to build an array, right? We build an array of nodes, and then every time we point, then we just directly do it by index. We point by index, and if we do that, BFS, DFS doesn't really matter that much. And of course, we can, yeah, like if it's seen, like when we make the connections, right? When we from here, and we make the connections for all its neighbors, we make the connections, and then we'll only go to the one that has not been visited before, because if something has been visited before, right? If a node has been visited before, then we don't go it, but we have to make the connection, but we don't have to go it. Is that right? So every node will be visited once, only once. Okay. I don't know what type of method I used in the past. I thought I don't have to create a separate list for this, but seems like that's the way to go. And regarding the actual method I'm going to use, I'm going to go lazy on this. Go very lazy, which means I will call def DFS. But we didn't have a memo, so I have a scene equals a set. Right, so we have to push a node and scene, right? And then this will not return anything. And for each node, let's say if node, right? If node, and node.val is our index, right? So we're gonna create copy equals node, right? Node for this in range. Oh, how many do you want? That's a good question. Well, it says only have 100. Number of nodes in the 100. So we just do 101, right? 1 to 100. We can iterate 1 to 100. Yeah. And if node, we say for neighbor in node, neighbors, node on neighbors, right? If, it doesn't matter if we just say copy node dot val is index dot neighbors dot append dot append. We need to append the neighbor, right? Append the neighbor. What is the neighbor? It could just be reference. That's fine. That's fine. So copy neighbor dot value, right? And now we say if neighbor is not in scene, actually if node scene.add node added to it. And if it's not in scene, we just call dfs neighbor and scene. Right? So do this. Once we're done, we're gonna return copy 1. Yeah, I'm not sure. This one, not very sure. Let's see. Example. See if it works. None type. v.append node.val. I don't have this. Oh, it just means it's not correct. How? No for everyone, right? And oh, I forgot to call DFS. Madre mia. Node and a set. Actually, I don't have to even set it. Huh? Still not right. Which part? Doesn't matter how many I created. Copy this is the node, right? It's the reference of the node. Well, actually that should be the node.val. .val, not in. Huh. Yeah, that shouldn't be an issue. Is it? Is it this one? You must return a copy of the given node as a reference to. What, is it not? These are copies. Oh, I didn't set a value. Huh. My bad. Val equals I. How about this? Val equals I. Yeah. So this one works, but stupid this one maybe. This one doesn't work. Next one works. And this one. Huh. Okay, so this one shall return empty graph. So I have this. A copy 1. Oh, it's empty. Now I see it's empty. What do we do when it's empty? If I don't have node, if I have node, then return 1, right? That's the node. If I don't have it, let's just do that separately. All right, let's just do that separately, which means we're gonna just check. Well, this is only 1, all right? It's a 1 node. So if the input node is an, what's the input node? Is that none? Yeah, the input node is none. So if input node is none, then we shall return none. In the current sense, we do not do that, which is sad, honestly. Oh, we'll just do this. If not node, return none. Right? That shall work for this case. Yeah. Try it. 600 days, but it was very bad. The runtime was terrible, horrifying. Yeah, I'm not feeling it. Honestly, I'm not feeling it. And for one thing, we're getting as many as we can, which I don't really think is supposed to be the way to go. Now, what we can do, right? What we can do is maybe change this into a dictionary, right? We change this into a dictionary, and we simply say for neighbor in this, right? So this or we can obtain the adjacency list first. So we create an adjacency. Basically, that's what we want, right? We want to create an adjacency list. Yeah, we want to create an adjacency list, and from there we can produce a graph. But that's basically what we're doing here. That's the adjacency list. It's just maybe it's not as efficient, which I agree is not as efficient. So maybe what we can do is we do this, okay? And then every time we traverse a node, right, we're gonna say if node.val is in copy, well, it's actually not in copy. If it's not in copy, then copy node.val will equal to node, right? And the value equals node.val. So we create a new one. And then for the neighbors, again, right? Again, this one we have created. And the neighbors start append. Now this one is something we have to do, which is the same, which is saying if neighbor.val not in copy, then copy neighbor, right, .val what equals node val equals neighbor.val. And then we can do this, and then we do this. So once we hit it this way, right, then we don't even need the scene because it's just a copy, right? That means something we have this. So we don't need this, right? We don't need this. I don't think we need this. And it's not seen, right? And then we basically just say, yeah, we don't need this. We just say if node.val is not in copy, we put it in, right? And if a neighbor in this, well, in this case, then it will never, if it's in it, then we don't even visit it again, which means we don't even need this. We always copy it, right? And then for everyone, blah, blah, blah. And then we say, right? But hold on. If we say every time we create a new one, that's going to be problematic because here we create a new one. Like if the neighbor is not in, we create a neighbor, but we need to visit the neighbor. So therefore, this one is still necessary, right? So if it's not in there, we're in there. And we visit this. And after we say if it is not in copy, if it's not in copy, which means we have not visited yet. But it's already in there. Nah. We still need a set. Because visited and copied is different concept. Right? we copy the neighbor, but we never visit the neighbor. So we have to use set. Unfortunately, I have to add node about, right? And then if it's not in scene, and we have to do a set here. Copy is this, which means this one ideally shall be a little bit faster. Okay, let's see if this one's slightly faster. Yep, this one's much faster in dictionary. So this is LeetCode. Let's see what method I used in the past. Oh, and I think this one probably is ready. Yeah, this one's ready. Well, we're on to page 7. Minesweeper. Ooh, I love Minesweeper. The game was quite fun. It's 133, right? Not sure if this is the best solution, but I don't think it is possible to rebuild, to copy, to clone the graph without preparing the cloned nodes in an addressable manner. Here I use a dictionary to address cloned nodes. And use DFS to traverse the original graph. Basically, we create an adjacency list, right? We create an adjacency list, but without actually building a list, but building a new graph. Yeah, that's how I put it. So it's ON because everyone is visited once, right? And it's 132 milliseconds. Ooh, 98. All right, so let's see. Discuss. Check out what I did in the past. Visit. And then visit. Node clone equals this. So I have a clone node. I have a catalog. Catalog is a dictionary, exactly. Catalog is a dictionary, like what I have here is a catalog. I call it catalog. We assign it. It's not in node catalog. I'll visit. Oh, I visit first. So I have a catalog for the current node, right? Which is the same as this, but then I don't put it in here. Right? I said I don't put it. I have the neighbor. I visit the neighbor first. So every time I visit a neighbor, I create a new node, right? So I create. Once I finish creating, right? Once I finish creating, and then what I do is handle I handle the connections. This is actually a better solution. This one is a better solution than this one. Well, for one thing, I don't have to use two, right? I have to use a set and have to use a copy. We can avoid using the set by using copy, by using this dictionary as the set. But to do that, we cannot do this, right? We cannot do this because this one will conflict, right? Whether so this it's put it inside the copy dictionary, but it has not been visited, so we cannot do that. But the easier way to remedy this is by not doing like these two lines, right? Not doing these two lines, and we do this directly, right? So this means every time a node is visited, we create a copy and then put it into. Yeah, this is a better solution. Cleaner, much cleaner. Come on, man. So this is my own old solution from myself. So this is the old solution from myself back in. What was this? Yeah, they probably use recursion. Maybe without hash map. 1020. 2020, 1020. It uses the copy dict as the scene set. The trick is to not assign, is to not create new clones during the neighbor iteration process, which means now we don't have to do this, we don't have to use this, we just go copy, and every time will be a new one, right? So we do this for neighbors, we don't do this, right? We don't do this, and then simply say if it's not in copy, then we visit it, after visit it, and then say this is the current, right? Our neighbors.append neighbor. Yeah, I think this one is what we need. Make up for all the wrong submissions from which day? I mean, maybe 2 days ago, right? 2 days ago we had a bad run. Yeah. Yep. Okay. Copies. What's copies? I have an ordered map. Yeah, we do have to have a map. I don't think we can do it without a map. Maybe we can. Maybe we can. I think Babichev has something to say. No, we need mapping. We need mapping. That's fine. All right, minesweeper. Oh, nice. Nice. They use the same graph. Beautiful. Oh man, minesweeper. I love this game. Oh, we can do online. Yeah, you can. Oh wow. Nice. I know this one and this one. Right? And this one and this one. Wow. Wait. How do I do this? It doesn't allow you to, huh? It It doesn't allow you to. That would be very slow. You have to like literally click every. Oh, I used to have controls. Hold on. Left click to reveal. Right click. Flag. Middle click. Or left right click a number to reveal its adjacent squares. Press spacebar while hovering to flag it or reveal its adjacent square. Press F2. Open the smiley face to start a new game. Wait, like this? I did. Wait. Oh, okay. 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 Yeah. I know this one. I click. Oh, okay. Hold on. Hold on. Hold on. Hold on. Oh, I can flag it. Oh, so I can do this. I can do this, and I can do this. All right, and then I have basically nowhere to go. Oh, what analysis, right? So this is one. So we have one among these three, and we need. So I cannot be one here and one here, right? Because I only have one. If one is here, then we need another one. It has to be. Nah, this isn't me guessing. Oh, bad luck. Wait, hold on. Okay, here. That being a 2, so we can do this. Do this, do this. 3, 1, 1. Oh, let's do this. 2, 3, all right? And then that's this. This. Okay, okay. And I don't know, this. I'm supposed to work on LeetCode, not doing this. Come on, man. 5, 2, 1, 2, 2. I remember there's a pattern, right? This is a 2, so I've only one is empty. Now hold on. These three has 1, right? So this and then has to be this. So this is not. My ability has dropped. Hold on. So we have 1 here, 2 here, and 1 here. All right, so we died. Yeah, I used to be able to figure out, like, there are patterns. All right, anyway. All right, we're given a matrix board representing a game. M represents an unrevealed mine. E is an empty square. B represents a revealed blank square that has no adjacent mines. 1 to 8 represents how many mines are adjacent to this revealed. X represents a revealed mine. So M is hidden. E is just unrevealed. B is a revealed blank square that has a blank. B is a blank. So digit is this. You're also given an integer array. Click represents the next click position among all the unrevealed squares. Return a board after revealing this position according to the following rules. If a mine is revealed, then the game is over. You should change it to X. If an empty square with no adjacent mines is revealed, then change it to revealed blank B, and all of its adjacent unrevealed squares should be revealed recursively. Alright, so we're just gonna update the board. Hold on. M is an unrevealed mine. Okay. E is an unrevealed empty square. B represents a revealed blank square that has no adjacent mines. No adjacent mines. B is a blank square with no adjacent mines. 1 to 8 is the number of mines adjacent to this revealed square, and X is a revealed mine. So if M is revealed, so click is to reveal, right? So if this is to reveal, then the game is over. We change M into X. If E is revealed, it's an empty square with no adjacent mines, then change it to B, and all its adjacent unrevealed squares should be revealed, so we have to go through them one by one to reveal. Should be revealed recursively, because if this is a blank, right? Yeah, so when you click on a blank, it will reveal the I see. If it's a blank, we have to go through, basically reveal every one of them, because that's not mine. It's not a mine, okay? If an empty square E with at least one adjacent mine is a reveal, then change it to a digit, 1 to 8, representing the number of adjacent mines. How do I know the number of adjacent mines? Because that's E, adjacent mine, or M, will have M, so count how many M's are around. But on the board, when no more squares will be revealed. Oh, this is interesting. So input is all E, which is unrevealed, and I click on 3, 0. Hold on, 3 zeros. 0, 1, 2, 0. Wait. Click on. Oh, 0, 1, 2, 3. 3, 0, which is an E, right? E is the empty. So when I click here, I need to recursively check this. And if it's a 1, then look great, honey. If it's a 1, then we stop, right? So this is a 1, then we. So 1 will stop. This will stop. But these keep continue. And this is unrevealed. Ah, very interesting. Wait, what if I click this? Yes. What if I click this? Oh, its input becomes this. Then I just reveal this, right? I don't do anything else. Yeah, I don't have to do anything else. Okay. This is fun. This problem is fun. The board is either M or E. And no, the board click. The click is either M or E. And what's the length of the? Oh, it's only one click. It's only one click. Okay, I thought I was gonna do multiple clicks. No, it's only one click. Oh. All right, let's try this. I mean, it's I don't have like a strategy or anything. You just code it, right? Just code it according to the logic. All right, just code it according to the logic. So what is the logic? The logic is follow the rules, and it's going to be recursion for sure, which I'm pretty sure we can just it's as if we make the click, right? Because the click, this is to review a position, right? We just call it to review a position. Like if we click here, right, and it's an E, so we mark it as E, then because it's E, so we do click on this, which is as if we do the click. So basically, um, the click, no, not E, my bad, it's B. It's a B, right? It's a B. So given this, we click on here. No. It's E. E is empty. Man, that's the hard part is to figure out what these letters stand for. E means it's empty. Okay, E means it's empty. So I make the click, and it's gonna be on the empty because it does say the click is either M or E, right? So which that doesn't make sense. It says it's either, okay. What's E? E with no adjacent. Wait, hold on. E represents an unreviewed empty square, so it will not click on a thing that is not E. Oh yeah, for sure. Because if you click on something that's not E, there's no recursion. All right, there's no recursion. You just review that one, and there's no recursion. So it has to be, right? It has to be. But in the check, right? In the check, we'll have the first check if it is right. We have the check. Basically, we have to say if, right? If board is an E, yeah. If board is an E, hold on. So do we have to put one for this? Yeah, we do. If you look at this, we have to put one, which means if it's already revealed, is a one, right? So before we click, we know what's underneath. We call the board click, right? We call it board click, and we will see if it's between 1 and 8. Then that's it. We don't keep doing. We don't do anything. If it's E, right? If it's M, we turn that into X, and we stop, right? And if it is a if it is a, how should I say, if it is a, so it's either number, right, or E, or B, right? Or it's E. If it's E, if it's a B, then we stop. So if it's either, if it's a number, right, or it's a B, then we stop. That's where the recursion stops. But if it's an E, if it's a mine, then we replace with X. Okay, these are all fine. If it is an E, we replace it with B, and we search around, right? We search and we try to click all those, okay? And when we click all those, yeah, think about this example. We click E, right? And then those are unrevealed, right? It's unrevealed, it's blank. The board is E, and if I click it, I change it to B. No, I don't change it to B because this is 1, right? We don't change it to, it's like, this is E, right? And then we click it, and I have to decide. I have to decide if it's a blank, right? So I click this, and if it's a mine, we know that. If not, like if, okay, again, go back again. The original idea is right. If B, all right. What if it's already a B? What I said, it will only click on the E, which is unrevealed, right? So we click this, and yeah, so that's what I know is to click this, and I have to go around, and then if it's a B, then we stop, right? And it stops, means it's been reviewed already. If it's 1, then we stop. If this thing itself is a mine, then we also stop and change it to x. So the only difficulty is in this case. So when we click it, right, it's an e, but we don't know which value we need to put into this, right? We don't know. So what do? We go through, right? We go through, and we need to return, all right? What do we need to return? We need to return whether this is a mine, right? Whether this is a mine, and then we go here. This return is not a mine, and I keep going, and if it's revealed already, right? So I'll go one by one. I go this, go this, go this. So when I go this, basically I click here, and I have to go this, 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 and I go this, and I have to go. I have to go this, right? All of this, but this one has been visited before, so I don't do that anymore. But this, and this, right? We all can visit because they have not been visited before. But I'll choose this one, and I'll go this, boom. But this one we have visited before, so we don't do. Then I click this, we'll go this, visited. We'll go this, click on this, and then go. These are visited. This is not being visited, right? This is not being visited. Do I visit that one? Holy guacamole. Hold on. It's not right. For every one I visit, I go through to check how many mines there are. Yes, that's the one. And there's no mines, this was set to blank, right? It's set to blank, and I can click. And this, the same thing. I go around to see if there's any mines. No mines. I click all of them. And this is the same thing. And then this one, right? This one, I go around and I find there's one mine. I change it to 1 and I stop clicking, right? I don't click. And I went back in here. We try to click this one. We don't click. I'm back in here, and then they're all visited, right? So this I'll visit. I don't visit. Okay. Yeah. This one. This is the one. This is the one. But how do we keep track of which one we have visited before? Oh, it's fine. Like if it's we don't have to keep track. We just like this, right? So we say click board, click 0, and click 1. If this is equal to B, right? I can just say current is equal to this. Okay, current equal to this. So we say if current is equal to B, or current is 1 to 8, we just return. I have to return. I can return the same thing. I'm going to change on the board. Huh. In this case, DFS, I don't have to pass board. I just need to pass row and column, I and j. Okay, I pass I and j. And current, I just call it I and j. I and j. Okay, if current is this, then we just return. Nothing to change, we're done. If current is equal to m, that's a mine, then we say board ij is going to equal to x and return. Okay. Otherwise, now we handle it as e, right? Now we're going to go around to check how many mines there are. So we're going to say, how do we go around? For Yeah, it's fine. We can actually do a 3 by 3. So we're just including the one in the middle, but I can significantly simplify. So I say for I, I cannot use I, P and Q. So for P in range, so be I minus 1, right? I minus 1 to I plus 1. I minus 1, I plus 1. I actually have to I plus 2. And for Q in range, J minus 1 to J plus 2. If, now we need M and N. M n equals lamb board. Didn't tell you it's a square, right? Nothing says it's a square. Board 0. And the board has to be a 1. Yeah, that's fine. So if, right, 0 smaller equal to P smaller than M and 0 smaller equal to Q smaller than N, and we don't have to worry about repeating because it's fine. Oh, we need to, I see, I can call it num minds, right? Or equal to sum for this, right? And then for this, so 2, 4, 4, and we just say this one, and this, and board P and Q is equal to M, right? So we sum this thing will give us the number of minds, and we say, right? We say, if num minds is 0, right? We don't have it. Then board ij, change it to, that's going to be a blank, right? It's going to be a blank, and we have to go around, which I think would be easier to say. If num minds is larger than 0, then board ij is going to be equal to num minds and return, right? Otherwise, we're going to set it to b, it's a blank, and we have to visit every one of them. I have to visit every one of them. Can we combine these two? How can we? We have to visit, I have to go through every one of them first. But what we can do is to get a list of, so I don't have to do this one more time. But, yeah, I guess it's fine. So we have to go again. Right? That's fine. That's fine. So, just exactly the same thing. I have to loop through it again. For P, for Q, if P is not equal to I and Q not equal to, but it's fine because I already set it to B, so this one will return immediately. So I can just say DFS P and Q. Can I? Yeah, that's fine. That's fine. Yep, and then we just DFS, click, destruct, click, and return the board. That's fun. Doing games is always fun. Oh, I can actually test it. Ooh, list out of range. What the heck? Out of course. Are you dummy? I forgot to check. Come on, man. Come on. All right. And P not equal to. No. I still don't like to do it there. I was going to say, all right, I'll budge. I'll budge. I don't want to budge. Where? Did I make the current and it? Oh, I think I did. Ah, oh, str. Good catch. Good catch. This has to be str here. How about now? Yeah, yeah, I think it should be good. You know what? I don't know. How about we do? How about we do? Because mn has to be 1, so we can do this basically, right? We can do e. Actually, I don't know how this one will go. So let's say 0 and 0. Oh, that would just be empty. That would just be b. Yeah. All right, I think that's good. Yep. Nothing too fancy. Nothing too fancy. So not a difficult one, but quite entertaining. The main trick is to understand when the recursive clicking ends. Well, it ends whenever the current spot, right? So whenever the current spot. Yeah, I just realized I don't have to because there's only one. I don't need to use the current that often. Right, the current spot. Whenever the current spot is B is revealed, has been revealed, which means it has the value B, M, or integer 1 through 8. So these are the anchor cases. Otherwise, we need to make sure whether the current spot marked by E is a B or a number. This means we need to check for the number of mines around the current spot. And after that, yeah, it's not after that. And then we simply recurse. If the number is 0, we mark current as B, otherwise the number of mines. Then we simply recurse. I don't know what's the runtime. Technically speaking, every node, every cell is visited once. So it's OMN. Score 254. Normal play. Okay. Let's see this question. I like this question. Very fun. It's the same. Alright, that will be it for today. Yeah, we had a very fun problem. And actually I want to play the game a little bit more. I'll see you guys tomorrow. Adios.